Hello everyone. Next, I will introduce the paper, Knowledge Distillation with Refined Logits. Knowledge distillation, also known as KD, compresses a large, complex teacher model into a smaller, more efficient student model by transferring the teacher's knowledge. Recent research on knowledge distillation has increasingly focused on Logit distillation because of its simplicity, effectiveness, and versatility. However, even high-performing teacher models can make incorrect predictions, creating an exacerbated divergence between the standard distillation loss and the cross-entropy loss, which can undermine the consistency of the student model's learning objectives. Existing correction-based distillation approaches consistently modify the teacher logits using label information. They either exchange the values between the predicted maximum class and the true class, which we called the swap operation, or amplify the proportion of the true class within the predicted probabilities, which we called the augment operation. However, such approaches may alter the correlations among classes. As shown in the figure on the right, we present an example. In this example, the image, labeled lion, is incorrectly classified as forest. After correction via the swap operation and augment operation, both operations disrupt the close correlation between lion and tiger. This disruption can obstruct the transmission of dark knowledge and hinder performance improvements. Therefore, we proposed refined Logit distillation, RLD. It consists of two novel distillation losses, namely sample confidence distillation, SCD, and masked correlation distillation, MCD. Sample confidence, SC, represents the binary distribution derived from the logits. It encapsulates the model confidence for each sample, thereby aiding the student model in generating proper confidence predictions for the true class without unduly restricting the distribution for other classes. In the context of teacher knowledge, one component of the SC is the maximum predicted probability value, while the other component is the sum of the predicted probabilities for the remaining classes. In contrast, the student SC consists of two components, the predicted probability for the true class and the sum of the predicted probabilities for the remaining classes. To transfer knowledge, KL divergence between them is calculated. While both cross-entropy and SCD operate on the true class, gradient analysis shows that their effects are not entirely identical. Consequently, RLD incorporates both, thereby endowing the distillation process with greater flexibility. Masked correlation, MC, denotes the probability distribution acquired after dynamically masking certain classes. This masking operation relieves the student model from aligning incorrect class rankings, thereby allowing the student model to generate very different output from the teacher, without incurring a large loss. Moreover, preserving partial class probabilities empowers the student model to learn valuable class correlations, consequently enhancing the model's performance. Specifically, the mask is dynamically derived from teacher logits and labels. We designate all classes whose Logit values are greater than or equal to the Logit value of the true class as the targets for the masking operation. Similarly, the distillation loss calculates the KL divergence between two distributions. On the CIFAR 100 dataset, our method achieves the optimal or suboptimal Logit distillation accuracy across all pairs. On the more challenging ImageNet dataset, our method achieves the optimal accuracy in all cases. More experimental results are reported in the paper. That's all for my presentation. Thank you.